Hello again. The goal of today's lecture is to be able to do depth first search algorithm, which is another popular graph algorithm, followed by strongly connected components. How to use depth first search to output what are called strongly connected components in a graph. So we'll begin with depth first search. Unlike breadth first search that we saw in the last module, depth first search is also meant to traverse or explore the vertices of the graph, but in a depth first way, right? So it goes deep down a graph as much as possible. It begins at a particular designated source like BFS, and then instead of exploring the adjacency list of that source fully, it takes one successor from that source, goes to that successor, then it picks up one successor of this successor, goes to that successor, and so on. So it goes deeper in the graph and first finishes exploring the graph to the deepest possible paths that it can trace from the source. Then it backtracks, comes back, and picks up the next vertex in the adjacency list of the source and goes deep down that vertex. And when it finishes going down for that vertex, comes back, picks up the next adjacency vertex adjacent to S, goes deep down. And when it finishes exploring the adjacency list of each vertex deep down, it finally comes back and colors S black. Right? So the goal of depth first search is also to traverse a graph and produce a tree. But unlike breadth first search, it goes deeper down in the traversal. Breadth first search grows breadth first in the traversal. Like BFS, DFS also keeps several attributes. It keeps the pi predecessor attribute associated with each vertex. It keeps a color associated with each vertex. It keeps two kinds of timestamps, unlike breadth first search. I'll tell you what they are very soon. But what does the pi attribute look like? Pi attribute basically is useful to produce or output the depth first tree, right? A set of depth first tree from different sources will constitute a depth first forest, and the edges in this tree are called tree edges. So as and when I explore the graph deep-wise, I set the pi attribute of each vertex that I encounter to be its parent, and when I consider all the pi attributes this way, I get the full predecessor subgraph, which happens to be a tree or a forest of trees based on whether the graph has one connected component reachable from the source or several connected components reachable from the source. Right? So like BFS, DFS also goes ahead and first discovers a vertex and then it also finishes a vertex. Now what we do is, unlike BFS, we keep two different kinds of timestamps here. A timestamp called .d, which is given when a vertex is first discovered, and which means a vertex which was originally colored white now becomes colored gray. And then another timestamp called .f, F for finish timestamp, which is given when the vertex is colored black, right? When the adjacency list of that vertex is fully examined. So obviously a vertex first needs to be discovered before its adjacency list is fully explored and the vertex is finished. So the D timestamp that is given to a vertex is always strictly less than the F timestamp that is given to the vertex. And the D and the F timestamps cannot be more than the number of vertices in the graph, right? Because that many paths could be there, assuming that the whole graph is connected, one for D timestamp and one for F timestamp. So they are basically values between 1 and 2 mod V. Right? So before it is given the D timestamp, the color of a vertex is white. Between when it's given the D timestamp and the F timestamp, its color is gray. And when it is colored black, we give the finish timestamp to a vertex. So here is how the algorithm looks like. I have split this algorithm across two slides because it wouldn't fit into one slide. So this is the initialization part as done for breadth first search. You start, for every vertex you color it white, you set its pi attribute to nil, right? If you remember in the BFS code, we also had set its distance attribute from S to 0. Here we don't do the distance attribute, we do the discovery and finish timestamps. For that, I need a generic variable called time, which I will use to set the .d and the .f timestamp. So I initialize the generic variable time here to be 0, right? So after I have done this, what I do is for every white colored vertex in the graph, I begin this procedure called DFS visit from that vertex. What does the procedure DFS visit do? DFS visit, first thing it does is increments the timestamp because it's beginning to search from a new vertex, and it says this new vertex from where I'm beginning my search, which is the vertex U, is discovered now. So it sets the timestamp that it is just incremented as the discovery timestamp for the vertex U. And because I'm going to begin exploring from the vertex U, which was white, I set the color attribute of U to be gray. Now I start exploring the adjacency list of U. So if there is a white colored vertex in the adjacency list of U, I have to color that vertex gray and then start exploring deep down that vertex V, right? So I pick up a white colored vertex, call it V, that is present in the adjacency list of U. And then the first thing that I do is I say U is the predecessor of V in my depth first tree because I found V as I was exploring U. Now I have to go down and deeply explore the paths that come out of V, right? So at V, I recursively call the same procedure DFS visit, right? So assuming that this code gets instantiated here, what would you do? You increment the timestamp. You say that the vertex V was discovered, set its timestamp, set color of V to gray, and go inside the adjacency list of V. If you find another white vertex there, you call the same procedure again for that vertex in the adjacency list. So this way DFS lets you go down the path corresponding to a particular vertex, right? And when you finish exploring all the paths deep down from a particular vertex U, which means you finished exploring this recursive call, when you come out of this recursive call for every vertex in the adjacency list of U, then you say, I have finished exploring the adjacency list of U fully. Then you color U black, increment the time, right? Time variable that you've kept as a global variable, and say that U is finished because it's colored black, and set its finished timestamp to be the current value of time, right? So we'll see an example to make it clear. What I have done is I've squeezed in the graph all in one slide. I hope you can read this, which is not what I did for breadth first search. Here I have squeezed the whole thing into one slide to make it better understandable. So here is this graph. You look at the top left corner. That is the given graph. How many vertices does it have? It has 6 vertices: U, V, W, X, Y, and Z, right? Unlike breadth first search, here, just for illustrative purposes, I have followed CLRS and taken an example which is a directed graph. This is the example from the same book by CLRS. So what I do is U is the source from where I begin my depth first search. Now if you look at this graph a bit before you start doing depth first search on the graph, you'll realize that the vertices V, X, and Y are reachable from U, but the vertices W and Z are not reachable from U. If you notice, there is no path, no edge that connects either of these vertices to W and to Z. So when I explore starting from U, I will be able to explore only these 4 vertices. And then I have to start my DFS search again fresh from W to be able to explore the remaining 2 vertices W and Z. And what will be the output of the algorithm? It will be a forest containing 2 trees. One with U as the root or the source of exploration, and one with W as the source or the root of the next depth first tree. So we'll begin with U. So what is this label inside U? Read it as 1/nothing. So there are 2 parts to a label. There is a numerator part. Think of this label as a having like a fraction, having a numerator and a denominator. The numerator part, the part on the top or the left side of the fraction, indicates the discovery time, the dot D time of a vertex. The denominator part indicates the finish time or the dot F time of the vertex. Right now, to begin with, because I'm exploring DFS from U as the source vertex, I say discovery time of U is 1 because I'm exploring. Not yet finished exploring the adjacency list of U fully, so no finish time is assigned to U. So the right hand side or the bottom part, which contains the finish time, is left blank. Now I explore the adjacency list of U. as per what the pseudocode says. How many vertices are there? If you see in this graph, there is V in the adjacency list of U, there is X in the adjacency list of U. I can choose either of them. This particular example, let's say we go to V. So V, which was originally colored white, now becomes gray color. Again, I have not depicted, like in BFS, I have not depicted the color of the vertices here. The gray color has not been depicted, just the black color has been depicted for clarity's sake. So I have discovered V. My timestamp has got incremented to 2. So I assign discovery timestamp of V to 2, and then I say this shade of this arrow indicates that in the depth first tree, U is the predecessor of V. The pi attribute assigned to V assigns the value as U. Right? Now what do? I have to recursively call the procedure DFS visit from the vertex V, which means I have to explore the adjacency list of the vertex V. In this example, it just so happens that there is only one vertex adjacent to V in the adjacency list, which happens to be Y. So I say I go there, Y has been discovered, I assign its discovery timestamp to be 3, and then I set the predecessor of Y to be V in the DFS tree. Now I start exploring recursively the adjacency list of Y. Right? If you notice, I'm going deeper in the graph. Right? I didn't bother after doing V to come to X because I'm not doing breadth first search. After doing V, I went to its successor Y because I'm doing depth first search. Now I explore the adjacency list of Y. What is there in the adjacency list of Y in this example? It's just X. So I discover X, assign its discovery timestamp to be 4, and set Y as the predecessor of X by putting the shade. So far the depth first tree that I have generated looks like this. It has these 4 vertices U, V, Y and X, and the edges of the tree are these gray shadowed edges. Right? Now I repeat the procedure. I have to look at the adjacency list of X. If you look at the adjacency list of X, what is the only vertex that is present in the adjacency list of X? That is V. But remember, V has already been discovered. So V is not colored white, right? So I don't go back and rediscover V, right? So I let it be. There is no other vertex in the adjacency list of this vertex X. So which means I have finished my exploring my vertex, my search from the vertex X. So I assign a finish stamp of 5, which is one more than the discovery stamp of 4. And then I color X black, right? I move on. I repeat this, and then I say I have come back to Y. The same thing, whatever was holding for X holds for Y. There is no more to explore. So I finish Y, color it black, assign a finish time. And then I move back to V. Same thing. I finish V, color it black, assign a finish time. Move back to U, finish U, color it black, assign a finish time. No more to explore at this stage. If you look at this graph that is labeled with J, I finished exploring the full thing. The remaining 2 vertices were not reachable from my source U. Those 2 vertices were W and X. So I start fresh once more. Depth first search from the vertex W. The last finish timestamp I had was 8. So I assign a discovery timestamp of 9 to W. Start and repeat the same exploration from W. In this case, I finish fast enough through all these edges because there are only 2 vertices, there's nothing more to it. And this path again leads to an already black colored vertex. So I repeat the same procedure for W and get this. So the final output of my DFS algorithm will be 2 depth first trees. One that has its root at U and has all these vertices. The gray colored entity is the tree that you draw out, and the next depth first tree in the forest has its root as W, and it just has these 2 vertices and 1 edge. So this is how DFS works. What is the running time of DFS? Let's go back and look at the code. This for loop which does the initialization takes mod v time, and then the procedure DFS visit, how many times does it run? It runs at most once for every vertex that is reachable through an edge in the graph from the source, right? So the initial thing takes order v time. DFS visit is called exactly once for each vertex. It doesn't call a vertex that is already colored black. So the loop in DFS visit, if you see there is one more loop here, this loop in this recursive procedure DFS visit runs at most this time, right? At most the cardinality of the adjacency list of a particular vertex. Sum of all the adjacency lists is no more than the number of edges, as we saw. So the total running time of depth first search is also V plus E. So depth first search also runs in time linear in the size of the graph. So pretty much it's the same as breadth first search. They have no difference except in terms of the convenience of what you want to use. I would ideally say that if you're not sure about what is the kind of graph it is, you go for breadth first search because it's a safer way to explore. If you go for depth first search, you might enter a loop in a graph that corresponds to the control flow graph, and the loop could be infinite and you may not be able to come out of the loop. So breadth first search is slightly better to explore a graph when you're not sure about the kind of graph that you're looking at. So towards showing correctness of depth first search, again, I will not be able to spend time proving the correctness of this algorithm. What I will do is walk you through the results that finally show that depth first search is correct. So what is the main correctness result that I want to show about depth first search? That is this. So when I take a graph and run depth first search on the graph, then depth first search explores the graph and it produces a forest of depth first trees containing tree edges or back edges. So towards that, I have all these theorems. So this parenthesis theorem basically says that the discovery and finish times of all the vertices are in proper intervals. If you see this example, right, I continuously increase. I first discover this time is 1, I next discover this timestamp is 2, then I next discover this timestamp is 3, and when I finish here, timestamp is 5, right? And if you see, if I go back and finish the vertex u, its timestamp is 8, which is greater than the timestamp 5. So this lemma says that if V is a proper descendant of a vertex u in the depth first forest, then the timestamp that is assigned, the discovery u is assigned discovery timestamp first, and then its successor descendant V is discovered. U is finished, and then V is finished, right? So there are 4 kinds of edges that depth first search returns. One is what is called tree edges, the edges that belong to one of the depth first trees. The next kind is what is called back edges, edges that connect back, that connect a descendant back to its ancestor, are what are called back edges. Forward edges are edges that follow the same direction as that of tree edges, but they sort of cut across several descendants and directly connect an ancestor to a descendant. All other kinds of edges are what are called cross edges, right? If you go back and take this example, this is the final output, right? Look at the last graph that my cursor is in. The final depth first tree is looking at it here. So the edges that are colored gray are what are called tree edges, right? This edge from U to X marked F is a forward edge because it connects U to one of its descendants X. This edge from X to V marked B is what is called a back edge because it connects a descendant back to one of its ancestors. Similarly, this self loop is also a back edge, and this kind of an edge, which is not a forward edge, not a tree edge, not a back edge, is what is called a cross edge, right? So DFS categorizes edges into 4 parts. Right now, the other thing that I wanted to do is to tell you how to use DFS to output what are called strongly connected components in a graph. So you need a directed graph to have strongly connected components, and if you have an undirected graph, you output what are called connected components. So what is a strongly connected component? A strongly connected component is a sort of a cycle in a directed graph. So it says a subset of vertices is a strongly connected component if every pair of vertices u comma v in that component, u is reachable from v and v is reachable from u. So if we go back and look at this graph that we had in this slide here, if you see this graph, this is a strongly connected component, v, y, x. All 3 of them are reachable from each other through this cycle that I'm tracing out now through the cursor. Similarly, just this Z is another strongly connected component, single vertex strongly connected component. If you see, W cannot belong to this strongly connected component because Y can be reached from W but not vice versa. So this graph has two strongly connected components, one that has this triangle and one that has this self loop. Right? So I want to be able to know how to use DFS to be able to output the strongly connected components in the graph, because I will use them to be able to look at prime paths and other entities for test case generation. So to do that, I look at the graph and I also look at its transpose. What is the transpose of a graph? You take the same graph and you reverse the directions of the edges, assuming that it's a directed graph. So the transpose of this graph in this example would be the same graph in terms of the vertices, but every edge will be presented with its direction reversed. Right? So I look at the transpose of the graph. One thing to note is that G, the graph, and its transpose have the same strongly connected component, right? Because if one vertex was reachable from the other in the original graph, then the same property would hold in the reversed graph. So I just go in the reverse way. They were reachable from each other in both directions, right? So to be able to output the strongly connected components, a standard technique to do is to be able to run DFS once on the graph, take its transpose and run DFS once on the transpose, but in the reverse direction of the finish times, right? So that's what the pseudocode does. You first run DFS, compute finish times for each vertex U, right? So that will give you a forest of DFS trees. Then you compute the transpose of the given graph. Now you run DFS on the transpose, but in the main loop of the DFS algorithm, you consider vertices in the order of decreasing finish time. So what it's intuitively saying is, if you go back to this example, after running DFS on this graph, I get something like this, right? Now what I do is I take the same graph, take its transpose. So I reverse the direction of every edge. So I get the sort of a reversed graph. So I run DFS once again, but in the reverse direction from the highest finish time vertex. So in some sense, this tree would have traced this. If I take this strongly connected component, what I'm trying to do is I'm trying to traverse one half of the strongly connected component through one DFS, and I'm trying to traverse the other part of the strongly connected component by running DFS once again on the transpose. That's what this code is trying to do. So how do you find strongly connected components? You run DFS on the given graph, record the finish times, take the transpose of the graph, run DFS again on the transpose graph, but in decreasing order of the finish times that you recorded in step number 1. And then what you do is that you output each vertex, because you would have gone through it once this way, once that way, both the ways of the strongly connected component. So each DFS tree in the DFS forest would be a separate strongly connected component that you can output. Right? So these are lemmas that tell you that the algorithm for running DFS is basically correct. So what they tell you is that you take the given graph, take all its strongly connected components. Let's say it has k strongly connected components. You collapse each strongly connected component to create a meta vertex. Right? So in this example, if I see, I told you, right? This is one strongly connected component. This is one strongly connected component. These two are standalone, separate strongly connected components. Single vertex. They don't have any significance, but they are like that. So what I do is I take this and I collapse and create one vertex for this, one vertex for this entire strongly connected component, one vertex for this, and one vertex for this. So I have 4 vertices. These edges get absorbed. These edges that connect these meta-connected, strongly connected components get retained in the component graph. So that's how I create the component graph. So I say vertexes are the set of vertices for each strongly connected component. There's one meta vertex. And I say if there is an edge that connects one strongly connected component to the other, then you put an edge in the new graph, right? This one says that if there are 2 distinct strongly connected components in the given graph, and I take a vertex path from one strongly connected component in the meta graph to the other strongly connected component in the meta graph, then there cannot be a path in the reverse direction. Basically what it says is that this component graph corresponding to a given graph where I collapse the strongly connected components into a single vertex is an acyclic graph, right? So using the fact that it's an acyclic graph, now what I relate is I relate the discovery and finish times, right? So what I do is in this particular lemma, one thing to be noted is that when I talk about discovery and finish times, I talk about the times that were recorded by the first DFS that runs in this algorithm, by the first DFS, not by the second one. right? So for an entire component, I say its discovery time is the least of discovery times of all the vertices. And for an entire component, its finish time is the highest of the finish times of all the vertices. So what I do is that suppose I have distinct strongly connected components C and C prime, then if there is an edge in the direction U to B, where U is in C and B is in C prime, then I say that C would have been finished, C prime would have been finished before C, right? So a corollary is the reverse. So it says that if C and C prime are distinct strongly connected components in a given graph, and suppose there is an edge from U to B in the transpose graph, then the reverse of that holds, right? So what it basically says is that if I run DFS once here, and if I run DFS once in the transpose, but taking it in the decreasing order of finish times, then I will be able to distinctly identify strongly connected components individually in this graph. Why does that hold true? That holds true because if I compose the meta graph, consider the meta graph where I compose and collapse each strongly connected component into one vertex, then that meta graph is acyclic. So if I had run DFS on that acyclic graph, I would have correctly done both ways DFS. Right? So the algorithms for strongly connected components that we saw here is basically correct. So to summarize, what I wanted to recap through these two modules was to teach you basic graph traversal algorithms, depth first search, breadth first search, and they have several different applications. Strongly connected components is one application. Similarly, you can do topological sort. Elementary graph search algorithms where you keep extra parameters, extra tags can all be done using basic manipulations of breadth first search and depth first search. And both these algorithms have linear running time. What we will do in the next module is to see how to use these algorithms to be able to define algorithms for test requirements and test path generations to satisfy the test requirements. Thank you.